These programs are distributed under a Creative Commons Attribution, Non-Commercial, No Derivatives license. You may copy and distribute these programs free of charge. You may not sell them, and you may not alter them. These programs are part of a study examining the value of podcasting as a medical educational medium. If this is the first time you are viewing a program in this optic series, send an email to jyoungmd@gmail.com with your name, position, institution, city, state or province, and country. Thank you and enjoy the podcast. Today's program is on prisms. In a previous podcast, we described index of refraction, and you'll recall that we describe the way that the ray of light bends with respect to the normal. So at the interfaces here between air and the glass or plastic of the prism, and then later on between the plastic of the prism and air once more, I've drawn the two normals, and I've drawn them as dotted lines. So we see right over here are is the dotted line that describes the normal in the interface between air and plastic, and over here again the normal between plastic and air. You'll recall that the ray of light, as it moves from an index of a medium of low index to a medium of high index, that the ray of light bends toward the normal. And this is in a previous podcast we described as similar to a skier encountering a patch of gravel. And the ray of light is seen here to bend from its initial direction in which it was going sort of up and to the right to a direction in which it is now going horizontally, because it is bent from its original path to a path that is toward the normal. And then as it exits the plastic, the ray of light bends away from the normal, as shown here, and this is similar to the car encountering a patch of ice. Net, what is going on? Well, first of all, let's give some words to what we're seeing here. The pointy top of the prism here is called the apex of the prism, and the flat base of the prism is creatively called the base of the prism. We see that the ray of light bends toward the base of the prism overall. So if we're viewing the way that the ray of light came in and the way of the way that the ray of light exits, net is bent towards the base. Now, by convention, we describe the orientation of a prism by the orientation of its base. So we would describe the orientation of this prism as being base down. Now, unfortunately, all of the interesting things that happened with a prism happen with its apex. So the ray of light may be bent towards the base, but if you look through a prism, the world as you see it through the prism is shifted towards the apex of the prism. Now, picture this. Maybe you want to bring your iPod actually into clinic in which you have access to prisms, and orient a prism base down in front of your iPod screen. Or maybe you can just visualize this if you're clever. Without the prism, if the iPod screen is directly in front of you, then there is an unbent ray of light, hypothetical ray of light. In this case, it's your visual axis. That is describes a path between the iPod screen and your eyes. Now, if we introduce a prism base down between you and the iPod, then this ray of light, or in this case the visual axis, will be bent down towards the base of the prism. And although the screen may have been in the center of your visual field before introducing the prism, what is in the center of your visual field as your visual axis is bent down towards the base of the prism may be the dial of the iPod. So although your visual axis is indeed bent down, what do you perceive? Well, you perceive the screen of the iPod, which had previously been in the center of your visual field, to have now shifted up. And the bottom of the iPod with its dial, which had been at the bottom of your visual field, to have also shifted up, now to the point that it's in the middle of your visual field. So although it is true that the ray of light, or in this case your visual axis, bent down toward the base of the prism, what you actually see is the image of the world being shifted up towards the apex of the prism. So most interesting things happen in the direction of the apex of the prism, not in the direction of the prism's base. Another interesting thing with the apex is that we correct tropias like esotropia and exotropia by pointing the prism with its apex in the direction of the deviation. So we would treat esotropia, in which the eye turns in, by pointing the apex in. Now, as I said, unfortunately, we describe clinically the orientation of a prism by convention by the orientation of its base. So we don't say we're going to treat esotropia with a prism apex in, even though that's, of course, what we're doing and what we're thinking. We say that we're treating the esotropia with a prism oriented base out. So anyway, that's the convention, and we need to abide by it. Now, in optics, as in all of physics, you're going to have a much, much easier time if you can keep your unit straight. And in all of optics, we will use exclusively meters. The exception being when we talk about prisms, and prisms we're going to describe in terms of centimeters. The amount of deviation of a ray of light you get in centimeters at a distance of 100 centimeters is equal to the power of that prism. So this is a prism that is bending light, of course, towards its base, 10 centimeters at a distance of 100 centimeters. Of course, 100 centimeters is a meter. This prism has a power of 10 prism diopters. Now, it is extremely important for us to keep our units straight. These are prism diopters. They are not diopters. So we do not say this is a 10 diopter prism. Diopter is a unit that we use to describe lenses and we use for vergence and has nothing to do with this. This is a 10 prism diopter prism. And if you want to be explicit in your description of this prism, you would say this is 10 prism diopters base down. We use the symbol for the unit for the prism diopter as either PD for prism diopter, but that's a little bit confusing because PD also can refer to pupillary distance when we prescribe spectacles, or we can use the Greek capital letter delta, which is the little triangle that's next to the 10 in this slide right over here. Okay. So let's look at what goes on in a prism. We have the ray of light that is incident. That is the one to the left of the prism here. And it strikes the interface and is bent towards the normal. This dotted line is not the normal. What I've done with this dotted line is just to extrapolate the incident line so that we can kind of see what is going on. And there is a certain angle of deviation here. There's an angle by which this ray of light is bent, and then it exits the prism. Again, angle here is theta sub 2. What I've done is I've drawn a second dotted line here parallel to the first dotted line so that we can kind of see what the total angle of deviation is for this ray of light, by how much this ray of light was bent in total by this prism. Now, it is the case with prisms that in addition to seeing what the prismatic power of a prism is, that the power is also a function of the orientation of the prism. And I don't mean just base up and base down. But if you tilt the prism a little bit, you will alter the prismatic power of that prism. So that if we take this entire prism and we tilt it, we will get more or less total deviation to the ray of light depending upon how we tilt it. It turns out that we get the least deviation if the theta here on entrance is equal to the theta here on exit. And we refer to this as the orientation of minimum deviation. Now, you'll see on the base of the prisms that you'll see in clinic is a little number that'll be stamped, 10 or 15 or 20 or whatever it is. And that is the power of that prism in prism diopters. But that power assumes a particular orientation. And unfortunately for us, the material from which the prism is made determines what the appropriate orientation for that prism is for the little number stamped on the bottom to be accurate. So plastic prisms, which are the ones that we will employ most clinically, are calibrated to be held at the orientation of minimum deviation. There is one prismatic orientation that has an eponym, and much to my dismay, it is not Young's position, but it is the Prentice position. And in the Prentice position, one of the rays of light, and we can think of it as being the incident ray of light, is oriented perpendicularly to the first interface. You'll note that the Prentice position is not the orientation of minimum deviation. However, the Prentice position is the position of calibration for glass prisms. So if we have a patient and we are correcting the tropia, in this case it's an exotropia, with a glass prism, we want to orient the glass prism in the Prentice position in order for the little calibration mark at the bottom of the prism to be correct, to be accurate, to represent what the prismatic power is that we're actually obtaining. So we'll have the back of the prism perpendicular to the visual axis for that eye, and this is the correct positioning for glass prisms. Now, as I said, the prisms that we're going to primarily use clinically are plastic prisms, and plastic prisms have to be held in the orientation of minimum deviation. And initially, this sounds like a very difficult thing to do, how to estimate where both angles are going to be equal, but it turns out that it is, in fact, very easy. If we define the frontal plane as the plane being sort of perpendicular to the direction of the nose, then the proper positioning for a plastic prism in front of the deviating eye is such that the back of the plastic prism is coincident with the patient's frontal plane. And if we do this, and you can look at this diagram a little bit and discover why it is in fact true, but it is, then the plastic prism will be held in the orientation of minimum deviation. Now, to think this through kind of one more step, sometimes someone's deviation exceeds the highest prism that we have in clinic, or perhaps we don't have a complete set of prisms in clinic. Perhaps we're missing some of the prisms. And let's say that we have a 10 prism diopter plastic prism and a 15 prism diopter plastic prism, and the patient's exotropia exceeds even the 15 prism diopter plastic prism. Well, what do we do in clinic? What you'll see people do, and I'm sure what you'll do too, is to take the two prisms and stack them up so that you've kind of made one big prism. And that's fine, but I want you to realize something. The prism that is coincident with the patient's frontal plane is being held in the appropriate position, the position of minimum deviation, which is the correct position for the plastic prism's little prism diopter mark on its base to be accurate. So let's say that that's the 15 prism diopter prism. The other prism onto which you have stacked the 15 prism diopter prism is not being held with its back surface coincident with the patient's frontal plane. So even though that prism may be marked with a 10 prism diopter mark, you know it is not being held at the orientation of minimum deviation. It's not being held at the orientation in which it was calibrated. And because it's not the orientation of minimum deviation, it has to be something more than minimum. So in this case, stacking a 10 prism diopter prism on top of a 15 prism diopter prism will give you a total prismatic power of, well, you solve it. Is it less than 25 prism diopters, 25 prism diopters, or more than 25 prism diopters? Well, the answer, of course, is more than 25 prism diopters. Because although one of the prisms is being held properly, the other one is being held at greater than the position of the angle of minimum deviation. So it's going to have a prismatic effect that is greater than what is marked on the prism. And in this case, 10 plus 15 is going to be some number greater than 25. Now, you can try this out clinically. If you pick up a plastic prism from clinic, or if you otherwise have access to a plastic prism, and you hold it up and you look through it, and of course, as we discussed at the beginning of this lecture, the image will be shifted towards the apex of the prism. If you tilt that prism back and forth, then you'll see the more you tilt it, the more deviation you get, the higher prismatic power you get. So stacking prisms will give you more power. It will, in fact, give you even more than is marked on the base of the prisms added up. Okay, so here is something about which many ophthalmology residents and trainees are asked, but has a utility that I believe is next to nil, which is this. For pretty much all reasonable deviations, the angular deviation is equal to almost exactly half of the prismatic deviation. So if someone has a 60 prism diopter exotropia, he has a 30-degree exotropia. Well, you know, it's only in very unusual circumstances that it is to our benefit to describe deviation in terms of degrees. But now you know how to do it. And this holds true for angles up to about 45 degrees, as shown in the diagram on the right side of the screen, which means that it holds true for deviations up to approximately 90 prism diopters. And I've shown you here that, for example, 58 prism diopters is equal to a 30-degree deviation. But from my standpoint, this is akin to ophthalmic trivia.